Hey, welcome everyone to this week's Physics Meets ML. We're very to have Nils Thuerey here today. Nils Thuerey is Associate Professor at the Technical University in Munich, and he focuses on deep learning methods for physical systems, with an emphasis on fluid flow problems. And beyond latent space simulations and generative models, he's currently especially interested in learning algorithms powered by differentiable solvers. And yeah, we're very happy to have him talk today about differential physics simulations for deep learning. And please feel free to ask questions at the end of the talk, or write them in the chat if you feel comfortable, and we can address them later at the end of the talk. So without further ado, please go ahead. Thank you.
All right. Thank you for the introduction, Sven. And thank you very much for inviting me to this seminar series. There have been a lot of interesting talks here already. And today, as mentioned, I want to focus on differential physics simulations in the context of deep learning. My name is Nils Thuerey from TUM. And let me start by motivating this topic a bit more broadly. So I'll focus on physical phenomena and simulating them in computers, and they're everywhere around us, as I hope all of you are aware. I'll focus on examples from fluid mechanics. Here we have that the air in the room around us, water that you drink from a cup, or classic problem, the flow around an airfoil. So there are numerous problems that come up and are very relevant for everyday environments in this area. Oh, now it's playing, right? Now you see the water splash here. They come up in all kinds of adjacent fields for robots interacting with fluids. This robotic fish is a very good example, very challenging and interesting phenomena. But even if you think about autonomous vehicles, they drive in the air, it becomes important. And the big point here is this comes up in many fields. Many of them I won't really be able to touch: thermodynamics, plasma physics, medical simulations. Our own bodies, our blood can be simulated in a very similar manner. And I'll focus in the following on problems that can be described with the Navier-Stokes equation. So here's a kind of short incompressible form, just to make sure I have them on the slides at least once. I don't want to go into details here, but in a way, I think it's a good and challenging model problem. We have advection diffusion terms here, hard constraints in terms of mass conservation. With the turbulence phenomena, it's very challenging. So this is a good starting point to explore this combination of deep learning and physics. And to summarize what I want to target in the following on a very high level, the goal of what I'll explain is that we actually want to keep these physical models that we have. They're very well established. They're great idealized models. And we have a long history of developing very powerful numerical methods. So both of these, I think, are definitely worth keeping as much as possible by all means. And now we have these new machine learning techniques, and especially deep learning being the most powerful one here. That's what I want to focus on. So in a way, that's for kind of cleaning up the remainder here. Sounds a bit mundane, but there are a lot of challenges left for the traditional methods, if you think about numerical errors or bridging this gap towards real-world phenomena. And I think this is where these methods are very powerful tools. Yeah, so I want to focus on this intersection here, and the methods that we encounter here can already be roughly categorized. And one good way to categorize them is the following one. We, of course, have our physical simulation. The traditional one here is a forward simulation. We set up initial conditions, boundary conditions, and then we can, for example, predict how something evolves over time. For many practical applications, we have inverse problems where we want to enforce some constraints or want to minimize a drag lift coefficient. In all these cases, we typically have some optimization loop around the simulation, and things become magnitudes or a lot more expensive typically, but in a way, both are still closely related. And no matter whether it's actually forward or inverse, we can distinguish how the learning process is coupled here. So the most only barely coupled, if you want, approach is what I'll denote as supervised in the following. This is basically just using the data. So all the learning is done with physical data, but in a way, there's no further interaction between these two halves of the picture. We can incorporate physical loss terms in the training process. That gives us some more feedback about the physics we'd like to model. But what I want to focus on in the following is what you could call interleaved, or what in the title was summarized with this differentiable physics keyword, meaning that ideally these physical systems and the deep learning process really work very tightly together. And that's at the core of what I'll be talking about. We're definitely not the only ones looking at this. We've been looking at it quite a while now, and this is actually just a selection of some of the other works that I won't have time to go into detail here. Just to mention it, there are a lot of other interesting approaches. I'll be focusing on two from my group, who were actually led by Philip, a PhD student, and Kiwan, a former postdoc in my group, together with collaborators. So this is what I'll be following, what I'll be focusing on in the following. And before going into the details here, I want to explain a bit what I meant with this differentiable physics in the title. It's arguably just a keyword inspired by differentiable rendering that simulates light. And here we're actually dealing with differentiable numerical simulation of physical phenomena. That's kind of shortened to differentiable physics here. And in a way, the key idea is inspired by this differential programming field, fairly simple. We have some model equations, some PDE in the following denoted with this P here, and some phase space states S that we can compute with these typically evolve over time. And the crucial ingredient now driving the learning and improving the learning process is that we have a gradient, dPds, that tells us how we need to change the inputs to this PDE in order to get the desired change in the output state. It's just a first order derivative, but of course, S can be high dimensional and not all of the solvers provide this, but this is the key quantity. Right, so this actually requires a simulator that can compute this efficiently, which is not always a given, but hopefully I'll be able to highlight that it's actually worth aiming for this. And also what I probably will come back to a few times in the following, it's not just this loss formulation. It's not just adding some residual loss to a neural network, but we really have a full simulator for our PDE. And the more the better, actually, the more we can simulate in a way. Yeah, so the goal being a tight integration of a full simulation and the learning. Yeah, with that, I directly want to come to the first example, this first paper here called Solve in the Loop, where we looked at learning to reduce numerical errors. So errors come up all the time whenever we go from a continuous formulation to a discrete one in a computer, which we inevitably have to do working in a computer. And the visual way to explain what's happening here is that we have some good accurate discretization, typically denoted here by this R for reference. And looking at temporal phenomena, we have some time evolution from T0 to the Cn state here in this blue bubble here. And now we can go ahead and approximate these references with a cursor, for example, with a cursor solver called the source solver in the following. So as indicated here by these rougher patches, right, this could, for example, mean we increase the spatial resolution, have much larger cells. We could use lower order methods to speed up things. Or variant would be that we only model part of the physics that our PDE is somehow reduced. But no matter what we do, if we compute the same solution from the same starting point as closely as possible, we can match it in this other space, we'll get, due to numerical errors and approximation errors, some other trajectory. So shown in this orange color here. So if we could stick to the reference solution, even with this, for example, cursor resolution in the source space, we would hope to get something like the blue line here, which we by construction typically cannot. And now the goal is we have, or we will be using this rough approximation on the right. So this is still always in the picture, even if we have a neural network. So we're not replacing these solvers completely, but we want to get these solutions produced by this source solver, as I call it in the following, closer to the reference version, the higher order or the finer discretization. Yeah, so this is the main picture of what we want to do here. So closing this gap towards reference, and typically this will be done by a correction function, taking some of the source states and being conditioned by a set of weights theta for a neural network in the following. So before going for this differentiable physics approach, let me just recap what the supervised version would look like in this context. So for a supervised approach, we would actually just use these solvers for the reference and source solution manifolds, basically sample them as densely as we can, compute different versions of it, do the same for the reference and the source. So then we typically would get some pairs that differ in the way shown before. And right from these, we could directly compute errors that drive a learning process. In this notation, this T denotes a projection of some reference state into the source discretization. And we could now train this corrector to basically learn an L2 distance in the simplest case between the source and the reference. So it basically should just, based on examples, fix the gap here. And right, if we do this, we get a gradient with respect to the theta, the variables. We keep on doing this until our process converges, and then we have a trained network. However, the problem here is that these trajectories I showed before actually updates over time. So if we do it this way, the solver or the corrector C will only always see these states produced by the source solver. So as soon as we start improving them with these corrections, they actually start to look different, and the solver will have, this corrector will have trouble giving us the right corrections. This is very simple to set up, but problematic. Also, to contrast the main approach with these physics-informed approaches with these residuals, in this case, we can also go in and train a neural network, at least now incorporating a part of the physical description of our PDE. And a neat thing about these physics-informed approaches is that we can use the analytic derivatives of networks to compute these residuals. And then by construction, these would actually give us gradients and corrections for the theta. But this is in a way neat, but computing the derivatives in this way means we are relying on the representation the network learned, and the derivatives might actually be quite far off. And also, as I hope it's pretty clear from this picture, this solver, the green arrow that produced these simulations, is nowhere in this picture. We're somehow using a deep learning framework to approximate these residuals, but there's no kind of regular numerical solver that is included in this loop. Hence, it's actually also difficult for these approaches to really work with a solver. And this is the goal of what I'm talking about here in the following. So we have this gradient with respect to S of our PDE solver. And if we target this and set it up correctly, then we can also put some thought into how to compute these derivatives. So as mentioned a bit in the beginning, we have very powerful numerical methods for all kinds of disciplines, for fluid dynamics and all the others solving PDEs, and very powerful, often very accurate and tailored methods to solve them. And we can directly reuse a lot of that to compute these derivatives. So that also typically gives us good derivatives then. And as a small note, it is sometimes convenient to use these deep learning frameworks and compute the derivatives using, say, TensorFlow or so. Because if you think about it, or if you look into them a bit more closely, in the end, they just do a lot of matrix vector multiplications or vector operations, and they have the gradients for all these sub operations. So you could just re-implement your solver in TensorFlow and rely on that. That's in practice often not a good idea because that will be very slow. These solvers typically store a lot of in-betweens, and theoretically this works, but in practice it's not something I would recommend, but rather that it's worth putting some thought into this and computing the gradients for the intermediates that are actually important, some larger steps in a simulation with a discretization of choice. Yeah, one good example is a Poisson solve that comes up a lot also in a pressure prediction step for fluids, for example. So here we have a Laplace matrix, and to compute a solution, we typically need to invert this matrix, say to multiply it with a incoming divergence. And now if we compute the derivative with respect to that output of that process, then that is just the same matrix. So if we have an efficient solver for computing this matrix inverse, we can reuse that same efficient solver for the backwards pass for the gradient. And hence we get typically a gradient calculation that can be a lot faster than relying on something that TensorFlow also would give us. So this is a good example of where this can pay off or will pay off very quickly if you do it right. And then once we have for some larger steps these gradients available, then we can rely on some deep learning environment to chain them together with Otto, the standard Otto functionality. That then typically is very flexible. So that is the simple part in a way once this is set up correctly. Yeah, so for the setup I just showed with these reference and source states, an interesting and important point is this time evolution. So that typically means that we actually compute multiple time steps, and meaning we apply our PDE solver multiple times, and over time we also hence have to apply our neural network corrector. That's indicated here by this n superscript, in order to get a solution for, in the simplest case, n steps of our simulation. And I'll denote these steps now that were modified by the neural network with a tilde, because it's actually important to train, to have these S tilde states at training time so that our neural network can see what the solutions will look like that the network itself produces. So it's a bit of a chicken and egg problem, if you want. We have a neural network changing the states of our system, and the network actually needs to see those states in order to be able to work with them. And this is exactly what you can set up with this process by having the solver in the loop. The solutions at the beginning will look like the standard source space, but over time start to change, move towards the reference states. And at training time, the network will actually get these potentially very different looking states and learn to work with them. So this is one of the key goals here. And then if you put it together into a loss function, it looks a bit unwieldy here, but in the end, we can again unroll this over multiple time steps. That's important to actually get this look ahead at training time. The more the better, effectively. And for each of those, just compute an L2 loss. Important bit being that we actually have the dependence on these change states in the learning. Visually, I think it's very clear. So we start out in the same way, but now we really run this whole source solver to produce a number of different states, each of them influenced by the neural network. We actually just working with additions here. So we're just adding some vector to our phase vector S. You could think about other polynomial bases or even changing resolutions or so. This is relatively flexible, but for our tests, the addition actually already typically was a very good starting point. This we do all the way to the end, typically the end being determined by how much compute power we have, because this really needs to be done for every single learning iteration. And now we have one rollout, basically one prediction of what our network would do with the solver. And now we can start computing the loss because we have reference states from this initial state that we started from. And we actually get one loss for the last step, can compute a first backwards pass through the whole solver, and also get a first update of our weights. And then, this actually now uses our hopefully nice discretization that we had for our forward solve. And then we can keep on updating and augmenting this gradient with the additional reference states that we have, and do this all the way to the very, well, we actually don't need to go to the zeros one. There's no information here, but at least for the last simulation step, we still get a gradient. All these are typically averaged to give us one update of our weight vector theta. And this is all happening in one training iteration, and then we continue with the next one. So you can already guess this is not cheap, but hence it's actually important to have a good solver here in the picture. And this really allows us for every learning update to explore what a simulation does and get feedback on how the corrections do in that setting. Yeah, so let me directly show some examples of how that works in practice. So we started with a very simple 2D case for fluids, a wake flow with some inflow at the bottom, a spherical obstacle, a set of different Reynolds numbers. And here you can see, in this case, same numerical methods, but different discretizations, 4 times finer for the reference. And the chorus version, as we can see here a bit at the top, actually barely resolves the vortex shedding behind the obstacle. The reference can resolve a lot more of the behavior here. And yeah, just to provide some numbers here in this dimensional space that we used, we got a mean absolute error of around 0.14 for these pure approximate solutions. And now we switch to the approach that uses a neural network, in this case trained for 32 steps every time. Visually, this already looks very close. And if you compute the error, it's actually more than a factor of 10 lower in this case. Being a very constrained setting, these error measurements are reliable, and the error very nicely decreases. And I can also show that in motion just to illustrate how it behaves. So here you have the original source simulation. Then keep in mind the middle one now has a neural network, but still uses the same source. It's the same input initially as a source, but now augmented in every time step by a neural network. I think these were 250 steps, and they stay very close to the reference. Or for a higher Reynolds number, same, the source loses all the detail, and the neural network learns to preserve over time how these forces should shed behind the cylinder. Yeah, so in general, this very constrained case works very nicely. And here, being fairly small, we could also test how much it pays off to train with more and more unrolling. So here you can now see this is now just a relative improvement over the basic approximate solution, the source space. So the pure supervised training already gives an improvement of 30%, but then because of this distribution shift, as you would call it in machine learning, the states starting to look similar from those used at training time, we only get to 30%. It doesn't improve any further. If you bring the solver into the loop with 4 look-ahead steps, much smaller than the 250s that we typically used, you do better. But in this case, training with 128 steps for every learning update gets the error down by a lot more. So in this case, we're really more than halfway towards the reference states in terms of L2 error, with a 60% improvement. So here, this really paid off even unrolling for very long look-aheads. Yeah, so one of the strong points of the setup is also that it gives an improved generalization, because in a way we have a split here between the workloads. We have this source solver that handles the rough larger scale dynamics, and then the network typically learns to refine smaller scales. It's also actually by construction, what we use here is a fully convolutional network that looks at neighborhoods, a bit like some finite difference stencil or so. And yeah, if you train it in the right way, then you can actually input very different input simulations and still get corrections that then, okay, I don't have a video for this case, it seems. Sorry, yeah. Oh, now it's playing. In this case, it was actually trained for different input configurations here. And in this example, also the solver is a different one. We're using a higher order advection scheme here for the reference to illustrate a bit that it's more than, you could learn more than just the change in resolution here. And this network, for example, generalized very nicely to different configurations of these smoke clouds. Hot smoke clouds are essentially simulated here. Yeah, or we also tried this in 3D. And one interesting thing that happened here in 3D was that the supervised version really diverged. So in 3D, we have a lot more complexity due to the additional axis of rotation. And here, over time, the solution started to look so different that the network basically produced just more or less random fluctuations, it seems, but did not learn to keep the simulation stable, basically. Whereas for at least moderate unrolling steps, in this case, it's more expensive to compute. The solver also was able to keep a lot of the vortex shedding behavior that should be in the reference solutions. So here you see, because of the increased complexity, larger deviations in terms of where the vortices form, but compared to the source inputs, which are very smooth and don't capture any of the interesting behavior, it's still a significant improvement, I think. Yeah, so it's worth a note here. So in the paper, we showed these simulations on a white background, and that looks like we are talking about fish smoking cigars here, but this is, of course, not the focus of the paper. What is worth pointing out is that in the end, especially if we only look at synthetic data, it's, of course, a question of runtime. And this is by no means the end of the line here. So we just, for the 3D case, measured some changes in performance. And here we were using a CPU-based reference solver, which took around 900 seconds for a certain time interval. And this combined, this hybrid with the CNN, in this case, took a bit more than 13 seconds. So this is a nice speed up already. However, I think, right, this is, you could probably achieve arbitrary speed ups here. Our CPU solver was also fairly optimized. And I think a very nice effect of using neural networks here is that these will benefit a lot from future hardware support. So if you think about recent CPUs being published, like the one from Apple, they have built-in neural engines or so that execute exactly these networks. So even if you have a pre-trained one, I'm sure that you'll see a very nice speed up of this unchanged trained model from future hardware generations. They can be executed very quickly. You could further try to prune and reduce the size. And the training times here are significant, but I think if you're in a setting where solutions need to be produced in a large number, then it's actually worth investing this training time once and then saving time when producing the actual solutions. So I think typically this additional overhead from the differential component here can in many applications pay off very quickly. Yeah, one other example that I think shows this is a bit more synthetic, but in a way shows this motivation a lot or very clearly is the following one. So this is in a way an even older paper where we started exploring this. And the setup here was that we looked at control. So we have some environment, for example, a room, and we have some fire that breaks out and it produces smoke. And now we have an exhaust system that we can control the inlets and outlets of this room, for example. And now we'd like to get the smoke out as quickly as possible. So in such a setting, it's really a question of real-time control, or it would be for a real-world scenario. You need to adjust these whenever fire breaks out to react to a situation. So we can't wait for weeks here to get an answer, but this needs to run very fast. And here, a trained network could actually be executed very quickly. So interestingly, the case here is quite a bit tougher than the first one. The first one relied on this first step supervision and interaction with the solver. And now we have a bit of a more abstract goal. So this is an inverse problem, right? We're starting with some initial conditions, smoke in a certain space. And now we want sometime later that the smoke ends up in another part of our geometry. And hence, in terms of neural network architecture, we also had to use two different networks here. So there's one network that predicts what will happen. And a second one that really acts, basically, that controls these exhaust valves, for example. And those two now need to work together to produce the desired output. But the second network here, this corrector, that's very similar to the previous numerical error corrector that I was talking about. It's actually trained in almost the same way. We have, again, this time unrolling. We have some horizon after which we want to achieve our goal, say n steps. So this we typically specified. And now one difference being we really only have a loss at the very end state. In a way, we don't care where the smoke ends up in between, as long as it gets to as it moves out of the window at the end. And this one feedback at the end, this is now what we backpropagate through all the previous steps. And from this, the network needs to learn to adjust and to control the physical environment over time to reach the state. So this is the added complexity here, and not really drawn in this picture, but you can now imagine that the second network is evaluated in conjunction and also actually trained end-to-end with the CFE network to, in the end, minimize the loss and reach the desired objective. So our simulation environment looked a lot simpler. So this is now the room I was talking about earlier. We have this fire being represented by some yellow blob of some marker density. So this is now also incompressible Navier-Stokes solve with 128 cells. And this ventilation now happens in the blue regions around the room. So this is what the network can control. And these are the windows through which it can basically push or pull air in and out. And the goal is now to move the smoke into one of the three openings at the top. So it's a very reduced setting, but it's trained in, apart from the second network, pretty much the same way as the first network. And also with this, the network actually learns to interact with the solver and push the smoke into the right. I'm not sure why the third one doesn't want to play. Now it's looking up into the right opening at the top. So this is, in a way, I think, a good example where we, in the end, need some system that potentially is evaluated many times in a real scenario and needs to run very fast, where it's worth one-time training a complex model and then to deploy it to some system. If you think about the setup here, it's actually also similar to reinforcement learning approaches, which are very popular and also powerful in their own right. But And this would actually be a very tough case for reinforcement learning. We have, in total, we had more than 5,000 continuous controls here that are set by the neural network in every time step, which for most reinforcement learning would be too much. Yeah, and with that, I already want to come to an outlook and summarize a bit. So I've been talking about these differentiable physics simulations with the goal of bridging simulations and deep learning approaches. Right, I haven't really shown the convergence plots or so over time, but at least from these few numbers I gave, you can see that they actually reach lower levels of error than reachable with other simpler approaches. They also give a better performance by approximating the complex behavior of a more expensive solver, and by interacting with this approximate solver, they typically also have improvements in terms of generalization. And the goal of these approaches is to show that it's really worth bringing together these deep learning and physical simulation approaches. I've focused on these two settings here with the numerical error corrections and the control. And there are many others. I think numerical weather prediction is in a way an obvious and very interesting, but yet of course also challenging next topic, where I'm sure this also will work very nicely. There it will be quite a challenge to get some simulator into the process, but as far as I know, there are already several groups working on this, so I'm sure we'll see interesting results there more or less soon. And we also by now actually explored these combinations in other settings, like partial PDE descriptions where we only have part of the picture, or turbulence modeling. And as a preview, I hope we can put these papers up very soon, but it really works very nicely in these other settings as well. So one thing, to summarize a bit the goals here, the message in short is to basically tear down the borders. There's no reason to have any artificial boundaries between the deep learning part and our simulators. So there's a very nice quote from Thuerey that I think, well, he of course was talking about the real world, but I think that transfers nicely to this setting. I think it's good to think of this as one country where the information, the data in terms of function variations F and all the derivatives freely flow between the different components. That really helps both the learning and the simulations. And in a way, of course, the important goal here also would be to improve our understanding of these physical phenomena. This might seem a bit surprising for people who are not deeper into this field to claim or aim for this. This is, of course, still difficult, but I think by now there is a very strong and I would argue well-founded hope that we can profit from the models that are learned. It's not just the black box. Our tools are improving, looking into what the models do, analyzing what structures they find. If you think about the Go neural networks, by now humans are training with these and learning new strategies from them. So I think this is a very important and interesting long-term goal. Of course, lots of work left, but nonetheless, I think an important one. And I've mentioned some papers that are not yet up, but I want to briefly mention that we do have some things which are up by now. So one of them is our 5-law library, which literally just minutes before the talk went online. So this is a differentiable simulation library, which was actually used for the examples I showed before. And this is the updated version of it. It's really tailored for these kinds of approaches. So one of the things which hopefully will be very useful are name dimension. If you use some of these frameworks, there's typically a lot of reshaping and kind of moving data back and forth. And here the solver basically knows about which dimensions are spatial, which are batch dimensions or additional channels. And this more or less gets rid of all the reshaping. It's also abstracting from certain from specific backends, and supports just-in-time compilation to get faster performance out of it. So if you're interested, please check it out. And also, last week by now, we released a larger collection of Jupyter notebooks in a physics-based deep learning book. And these also, I recommend checking out. Right, book in this case doesn't mean stack of paper, but it's really meant as an introduction and overview with hands-on examples in the form of Jupyter notebooks. It's all available online. So if you're interested in these topics, there's actually, for both of the examples I talked about, there is a Jupyter notebook with which you can run that on the spot in Colab. You don't need to install anything. This should run out of the box. By now, I think we have a nice coverage of some basic topics, but we'll also keep on extending and improving this document. So we definitely have a lot of plans for it in the coming months and years. And with that, right, here's the link if you want to check this out. I again want to thank my collaborators here, Philip Kion, and also Vladlen, Raymond, Robert, and you for these works that I've shown before, and Intel and ERC for funding, and thanks for listening. I'd be happy to answer questions.
Yeah, thank you very much.
Raised hands.
Yes, thank you very much, Nils, for this very interesting talk. I see a raised hand by Michael Chertkov. Please feel free.
Yeah, thank you. Hi, Neil. Yeah, great talk. Yeah, so I would like to ask you to comment on feasibility of extending your fantastic work to Lagrangian solvers. And I know that you've been working on PIV. So if you can maybe comment on particle image velocimetry, if you can maybe comment on how what you told us today is linked to this other part of fluid mechanics world.
Right, thanks. That's a very good keyword. All the examples I've shown have been using Eulerian discretizations. We've, for simplicity, basically worked on image-like data, typically actually, right, Cartesian grids. In a way, this is motivated by the good support in deep learning pipelines at the moment. This out of the box with the kind of regular image-based convolutions works very nicely and in a stable manner. I think in a way, these should transfer over to Lagrangian solvers. We've looked a bit at SPH-like solvers with some spherical particle kernels. We had a paper of using what we called continuous convolutions that transfer this convolution picture to particles. Basically, then the network learns different weights of mapping weights being mapped into a sphere around the sampling locations. And if you have a differentiable Lagrangian solver, I think it could be integrated in pretty much the same way. Or potentially, of course, also these graph neural networks, which in the end then couple with additional fully connected layers and perform some message passing steps over neighborhoods. So I think there's, or I believe that this also will work together very nicely. But right, this would be very interesting to try. We haven't had time to do this, but I think it's a very good idea.
Are there any direct further questions? Please feel free to raise your hand, but we can also go look at the questions in the chat. Do I see a question by Neil Fessel?
Does this solve the turbulence problem? No, not yet. Not yet. This is a nice millennium problem to solve. No, the millennium problem is on the theoretical end, of course, but I think it can definitely improve turbulence modeling. I think this is very promising for turbulence models. We've started looking at this, right? Unfortunately, I cannot show this yet. There are some interesting other works also by the people from Google, Harvard, for example. So I think this is definitely very interesting and promising direction, but the turbulence problem is definitely not yet just solved by this. So this will, I think, also still be quite challenging. So very interesting direction, but definitely not yet solved. The next question was the time scale of the 128 steps for the case I've showed before. Right, this is way larger than the eddy turnover time. So this is, I think, around 2 or 3 cycles. So this should nicely cover the full range of behavior. However, it's in a way also a good point. This eddy turnover time is, of course, a key length time scale here for these simulations with the vortex shedding. It's important that the solver basically sees the whole behavior, but irrespective of that, it's also in a way good, or the more time evolution the solver sees, the better. So independent of how long or short this is, you can think of it as a per step error or drift that the neural network introduces. And basically, the longer you can let the network see how its influences evolve over time or change the time evolution, the better. So in a way, I think, right, for these unrolling cases, I would guess that in a way, it's really the more the better. The more time you can invest into computing this look ahead, the more the network will learn to keep the simulation in the right direction. Next question was about the simulation, the reference being run in parallel. So the reference, also a good point that I didn't really clarify before, but the reference doesn't need to be differentiable. This could be seen as a black box. We get this data somewhere, but we need to be able to run this the source simulation, the approximate version, in some synchronized way to it. So no, this was not run in parallel. This was pre-computed. Only the source needs to be differentiable and ideally also run on a GPU for good performance. And no, it's not fair. However, in this case, comparing CPU and GPU directly, however, GPUs roughly have a factor of 10 faster memory. Most of these algorithms are memory bound. And even if you factor out this 10 times factor, you're still left with a 6 times speed up here for the case I've shown. And I think this could be a lot larger for other solvers even. Yeah. All right, then there was a question about to what extent a transfer learning is successful. I'm not sure I understand the question. So transfer learning in the deep learning context typically means that we use some pre-trained model and use it in a very different context. Right, you use a VGG model and use it to analyze videos or recognize faces or so. So in a way, we are not really doing that here. We know that we want to train a network that should work with the source solver, and the better we know the scope of the simulations we want to run, the better.
I think it's specified below as well,
okay.
just to highlight it's regarding different initial conditions, for instance.
Okay, so this generalization, yeah. All right, so in a way, it's not really transferred to new cases, and also I think it's important to mention, right, there's no magic here. The network can learn to work with what it sees. So it's typically for practical applications important that you actually train with data that is as similar as possible, by all means, to what you want to use it later on. However, if you train with such a solver and you basically let the network see typical local configurations, then it actually usually generalizes very nicely to new configurations, or you could also train for different boundary conditions or so. But it's typically important to have the changes in the training. So if you always let the network see one kind of boundary conditions, then I would expect it to not work well with new ones. But if you change the boundary conditions at training time, at least in some way, then this should work quite well with also boundary conditions it has not seen exactly in this way before. Yeah, the next question is actually a bit related to Michael's question in the beginning. So irregular meshes, right? I also don't see any reasons why this would not work. We've worked with, so even with these Cartesian grids, you can actually very nicely work with mappings. So as long as you can somehow map your data onto a quad mesh, it doesn't need to be a Cartesian one, then CNNs are really powerful. But if you really rely on very, very adaptive sampling, then that might be a good way to go. I think this is quite orthogonal, as mentioned before. If you want to use particles or different discretizations, in a way, it stays the same idea. You can use a differentiable solver of your choice with that discretization and combine it with your GNN. So I think that's a good idea. Typically, they're slower and more difficult to set up, so we focused on the grid-based ones here, but I don't see a reason why this would not work. All right. The next question is about the matching the accuracy. That's a good question, right? No, I have to admit, I don't have that number, because you're right, it's a good point. The comparison I've mentioned before with the 60 or 6 times speed up, the reference is, of course, more accurate. But also, as mentioned there, I think you could have arbitrary speed ups. It depends a bit on your solver and also on the gap you train for. So I don't have the exact number for that case, but I'm also quite certain that will find many cases when practice you can still get a better accuracy for performance. Yeah. Then there's a question about the core solvers being used in the neural networks. Right, so that is a bit the central idea, that we integrate such a coarse approximate or source solver, as I called it before, into the neural network training, which maybe most of you have heard also relies on gradients to update the weight of the neural network. And if we have a similar gradient for the physics part, then this is a very convenient and a very suitable way to couple the two. Right. Again, towards the Lagrangian direction, exactly, you can use your favorite graph convolution. I think that that should work nicely. Then there was a question about the unsteady wake flow. So it did generalize nicely to new Reynolds numbers, at least in the range of our solver, which, however, was fairly dissipative. So especially for the larger ones, I think it was quite bounded. And this wake flow was actually not trained for any changing geometries. So this solver would not generalize to, or we didn't properly test it, but right, I'm certain this would not generalize well. However, by making the model a bit larger and actually varying the geometry, I'm sure this model could be trained to also work with different geometries. So I don't see any inherent problems. But this buoyancy case, we actually changed the initial conditions and there it worked nicely. Yeah, and then there was a question about the temperature gradient. Actually, no, this we had a simple, the smoke had a simple buoyancy model, but for the fire, we assumed that it's basically a passive smoke. Then there is a question about a reduced order model. So no, actually, we're not using any ROMs here. It's also an interesting direction, but what I talked about does actually not really aim for reducing the size of the representation. And remeshing is a good question. There are some interesting works exploring that already, as far as I know. And I think ideally these would also profit from actually being able to train together with the solver as a kind of oracle to tell you where to refine or coarsen a mesh. So this would also be an interesting direction. Uncertainty, we have not looked at in these models, but you could actually fairly conveniently couple similar approaches with, for example, BNN, a Bayesian neural network approach. So if you use we've actually experimented with this a bit, some flip out layers, then you can also get uncertainty estimates from these. However, right, the BNNs are still tricky to use. So it's those, due to this uncertainty dimension, become pretty tricky to train. And analyzing them is also a different question, but theoretically, you could couple this with some Bayesian approaches. Then there's a question about pins and the discretization, right? So I would actually argue that pins, because we're working in a computer, also have to somehow discretize a solution, right? In a computer, we have in the end zeros and ones, so it needs to be discrete. We're forced to be discrete on some level. You just don't have any control. You're kind of letting the network adjust the weights and somehow figure out what the solution might look like and where to refine it. So it's a bit what I alluded to with the comments about the discretization. I personally think that it makes sense to use our understanding of the physics to do the discretization properly. If you have a boundary layer and you want to resolve it, then right, it makes sense to put a lot of degrees of freedom near the surface of an airfoil or so. You can wait for a network to find that out by itself after long training time, but also from our tests, this is quite tricky. So overall, the pins work very differently from what I've described. It's typically not simple to merge them with the solver. So from our experience, at least, I can recommend relying or basically thinking about the problem, using some human knowledge about how to model a problem in a computer, how to discretize it, and then use that knowledge to couple it with deep learning rather than hoping that the network discovers this by itself.
Okay. There were lots of questions in the chat. It was really nice to see.
Yeah, right.
Are there more questions?
Thanks everyone for asking and for joining.
Yes. I think, yes. So I think we have answered all the questions. So I can stop the recording now.